Okay, in this subtopic we're going to look at radioactive decay, and the major part of it, the first thing we're going to look at, which is going to be most of this topic, is that we are going to look at the different types of radio decay. Let's get into it. So in the last video we explored the structure of the nucleus, and we explored, if you like, the battle between the strong nuclear force trying to hold the nucleus together and electrostatic repulsion trying to push the nucleus apart, push all those like positively charged protons apart. And in the case where the strong nuclear force won and was stronger, we would get a stable nuclei. That would be one that would last forever. And in cases where the electrostatic force was too strong, those nuclei would eventually decay. And that leads to the release of radioactive particles. And we're going to explore those particles and those types of decay that can occur more. So if we just start with this graph, which is a graph of the number of neutrons versus the number of protons. So it's basically a graph showing all the various isotopes of the element. Each little square represents an isotope with a certain atomic number and then different numbers of neutrons, which is by definition what an isotope is. Now, if we get out into this area out here, past 82 probably, 82 is stable, from 83 onwards, the nuclei will not be stable because they are basically just too big. You cannot have, the strong nuclear force can't hold the two edges of the nuclei and the oppositely charged protons on those two edges together. So what happens there, and we're going to go into this in more detail soon, is it reduces its size by emitting a helium nucleus, which contains 2 protons and 2 neutrons. This is called alpha decay. As I said, we'll get into that in a minute. This region here, where all the blue dots are, we have basically high numbers of neutrons. Too many neutrons. What happens here is a neutron is converted to a proton, releasing an electron. So we reduce the number of neutrons by 1, we increase the number of protons by 1. That pushes this ratio across this way really, but down. Actually it pushes it this way. No, it pushes it this way because the neutrons decrease and the protons increase. In this orange region down here, we have too few neutrons. And basically what happens is we need to make another neutron. So a proton is converted to a neutron, and we also get the release of a positron. This is called beta plus decay. So beta plus, beta minus, and alpha, blue, orange, yellow, they're the 3 main types of decay. There is some other types of decay that happen which are rarer. We're not going to worry about them in this course or even next year. Just before we go on, if you haven't already, I strongly encourage you to have a look at this video, Stable and Unstable Nuclei from Fuse School, which in a more graphic way goes through what we are about to discuss. So the first type of decay we're going to talk about is alpha decay. So if a heavy nucleus is unstable owing to an excess of nucleons, so basically we have usually there we're talking about an atomic number greater than 83. So excess number of nucleons, basically Z, which is the atomic number, is greater than 83. The atom will decay, and when it decays it will release a helium nucleus, which is what we know as an alpha particle. So this is the helium nucleus here, or the alpha particle, and you can see from here atomic number of 2, so it has 2 protons, and it has a mass number of 4, so it must have 2 protons and 2 neutrons. So I always think of this, it's a bit like a weight loss mechanism for fat atoms. When they lose weight generally by losing these alpha particles. So we start off with the parent nucleus, and it loses basically 4 nucleons, so 2 protons and 2 neutrons, and we get left with a new isotope, the daughter isotope, which has an atomic number of 2 less and a mass number of 4 less. So let's look, because it might make this simpler to understand, at a couple of examples. I know I was talking the other day about this one. Sorry, I get a pen. Uranium 238. This is the most common naturally occurring form of uranium. It has a very long half-life. The half-life is about 4.5 billion years, so that's why it doesn't decay very fast, but nonetheless it will always decay. This isotope is used, I know, in a radioisotope thermoelectric generators, which is the power sources they use to power lots of spacecraft that are being sent to distant parts of our solar system. It's also the one of the main reasons the centre of our Earth is so hot, and we have basically molten rock within the mantle, because as this decays, it also releases some heat, and that heat is trapped by the crust of the Earth, and that's what keeps the core of the Earth so hot. But that's a little bit off task. I guess that's just why it's important. What happens is when that decays, obviously it releases an alpha particle with an atomic number of 2, a mass number of 4, and the other particle that gets released, we can work out here, would have an atomic number of 90, because it's lost 2 protons, so it's going from 92 to 90, and a mass number of 2, 3, 4. And if we check our periodic table, that would be thorium. Now, thorium is also greater than 83, so that will decay, producing, I think it is radium, and then radium will decay, and so, and it'll keep going till you get normally to lead, which has an atomic number of 82. We'll talk later about how they use this fact to date rocks, because we can look at the amount of uranium versus the amount of lead, which is formed from the decay of the uranium, to get an estimate of the age of rocks. Not going to go into that now, though. Another one that you may be familiar with, I guess, but not realise you're familiar with, is americinium 241, and americinium is element number 95. And you're going to me, I've never heard of americinium 241, but I can trust you. If you look around the room, there is probably some in the room. That, again, is atomic number greater than 83, so it undergoes alpha decay, releases an alpha particle. We get something with a atomic number of 93 and 237. If we take 4 from 241, and 93 is neptunium. So, if you haven't worked out yet, the americinium 241 is what's in your smoke detector. So you have a radioactive source in that smoke detector, and it's constantly releasing these alpha particles. However, if some smoke gets in there, the alpha particle, it's americinium's constantly releasing the alpha particles, and there's a detector, and they're picking up these alpha particles. However, if some smoke goes in there, the alpha particles hit the smoke rather than the detector, and so when the detector stops getting as many alpha particles, it knows there must be smoke in the room, and it starts going beep, beep, beep. You know the sound a smoke detector makes when it goes off. So, another bit of, hopefully not so useless information for you. Anyway, that's alpha decay in a simple sense. There is a little bit more to it that we'll get to at the end, but let's just do this step by step. This is what happens, with atoms that are too large. Okay, let's keep going. So now we're going to look at beta minus decay. Beta minus decay occurs when a nucleus has an excess of neutrons and involves the conversion of a neutron into a proton. So we get rid of a neutron and we turn it into a proton. This is accompanied by the emission of an electron and an antineutrino, and we'll briefly explore why those particles are also released. So within the nucleus, what happens is one neutron turns into a proton, and we also get an electron released. This -1 is this way of saying it's got a -1 charge, because a proton has an atomic number of 1 and it's got a positive charge, so it's like a +1. A neutron has an atomic number of 0. There's no protons in a neutron, if that makes sense. So this notation is just a way of indicating both the charge and the mass number of these particles. The mass number of an electron is effectively 0 compared to a proton or a neutron. So you can see in this process, neutron has no charge. We produce a proton, which has a +1 charge, and an electron that has a -1 charge. 1 plus -1 equals 0. So charge is conserved. All good. Now, if we think about what's happening within the actual overall, so now that first equation really just looked at what's happening to one neutron. We start off with a parent isotope, and what happens is we actually get another proton form. So the neutron turns into a proton, so the atomic number increases by 1. We get an increase in 1 in the atomic number for the daughter nucleus. The mass number stays the same. We don't gain or lose any nucleons, so the mass number stays the same. But as said here, to balance out the charge, we get the release of an electron. However, there's a little bit more to the story. Early analysis of the products of beta decay, both minus and plus, which we'll talk about in the next slide, revealed energy and momentum was not conserved. So they couldn't explain where all the energy and momentum went. Don't stress too much about what they are at the moment. We talk more about them later in the year. To explain this, the concept of a neutrino and an antineutrino was proposed. During beta decay, a neutrino with a complementary amount of energy and momentum corresponding to the electron is released. Further experiments by physicists prove the existence of a neutrino and an antineutrino. So basically, when they first looked at decay and they looked at the energy, they went, this doesn't all add up. What's wrong? So someone said, there must be another particle that we haven't discovered yet. Let's call this an antineutrino in the case of beta minus decay. And once they proposed this particle, and then basically a group of experimental physicists went away and they were able to discover this particle. Now, this is a bad analogy, but I think it sort of works. A neutrino doesn't have any mass, so it's a little bit like an electron. It has an insignificant mass, and it has no charge. So you can loosely think of a neutrino as like an electron with no charge. Now, it's a bit more complicated than that, but for this level, if you think of a neutrino or an antineutrino as like an electron with no charge, that's probably a good mental picture to have. So let's look at a common isotope that undergoes beta minus decay, and probably the most common one we deal with is carbon-14, used for carbon dating and other things we'll talk about potentially later on. So what happens when that undergoes beta minus decay? Well, firstly, we get a neutron turned into a proton. So we have one more proton. So we have an atomic number of 7. That makes it carbon turning into nitrogen. But the mass number stays the same. The total number of nucleons is the same. That hasn't changed. And then we get the release of an electron, no mass, and a charge of -1. So we do that with the sort of -1. You will, in some places, see that written as a beta minus particle, like that. That's just an alternative way of writing the same thing, so you may see both. Don't get too fussed. Plus, when we have beta minus decay, we get, we get an antineutrino formed like that. So, hopefully I have described the structure of nuclei that causes each type of beta decay. So this is where there is too many neutrons. We've written equations for the decay here and here. Use the conservation of charge to explain the emission of an electron. Talked about that here. Use conservation of charge to explain the emission of a positron. Okay, that's in the next one. We'll talk about that. So, hopefully you can see how we've ticked all these success criteria here. Okay, let's keep moving and talk about beta plus decay. So beta plus decay occurs when a nucleus has an excess of protons, so too many protons or alternatively not enough neutrons, and involves the conversion of a proton into a neutron. So we decrease the number of protons, increase the number of neutrons. This is accompanied by the emission of a positron and a neutrino. So if we can think about in the nucleus, we have a proton converted to a neutron. To conserve the charge, this has a positive charge, this has no charge. We need to get this positively charged electron released, which we call a positron. You can see here the charge on a proton is 1, the charge on a neutron is 0, the charge on a positron is +1, so 1 equals 0 plus 1. Hopefully that mass isn't too difficult. In a general form, we basically lose a proton because it becomes a neutron. So the atomic number decreases by 1. That's Z minus 1. It decreases by 1. And as I said, we get the positron and the neutrino. So let's look at a specific example. Let's look probably at, let's stick with carbon, but instead of going to the higher ones, let's go back to carbon 11. So that would have 6 protons and 5 neutrons. It's basically got more protons than neutrons. When it decays, we will get only 5 protons left because one of the protons is turned into a neutron. That makes it boron. Still has the same mass number, 11. Plus we get released the positron. Plus we get the neutrino released there. So I might label that here. That's a, I'll use a different colour there. That there is a positron because that is a new word to us. And again, some places rather than it written like that, you'll see it written as a beta plus particle. And I've just realised I missed off a 1 there. +1. So yeah, that is beta plus decay. So you might think, the picture is complete. However, there's one more thing I need to tell you about in a minute, and then we will be almost there. So following alpha or beta decay, whether it's beta plus or beta minus, the daughter nucleus that's formed, or even the alpha particle for that matter, are normally left in an excited high energy state. And basically what happens is they decay or they relax, I guess, releasing high energy photons of light known as gamma rays. So whenever we get any of the decay we've talked about, whether it was the I've forgotten already, the thorium isotope that produced, or the Neptunian isotope, they will be in not their most stable arrangement. They'll be in what we call a high energy state. They won't be arranged as nicely as they would like to, and they will basically rearrange to a more stable, and that energy, that excess energy that was in them, will be released as these photons of light, very high energy light, known as gamma rays. So if you want to get an idea of how much energy is in these gamma rays, we talk about visible light, red, orange, yellow, green, blue, indigo, violet, Roy-Jabiv, the spectrum. We know if we go past that, probably we get ultraviolet that causes sunburn. If you get more energy into the light than ultraviolet, you get into X-rays. X-rays can see through our skin. If you go to even more energy than X-rays, then you get into the gamma rays. So they're a very high energy form of light. So basically the way we sort of tend to show this, I'm going to use an isotope that's used a lot for medical imaging, which is molybdenum 99, and molybdenum, I'm going to have to check, is number 42. This, to show it's in an excited state, we use the little star there. That's a way of showing it's in an excited state. And basically, this will relax, rearrange itself and relax is probably a better way to say it. So it'll still be molybdenum, but it won't be that high energy state. And when it does that, it will release a high energy gamma ray photon. So that little symbol that I've got there, that might be new to you, that's from the Greek alphabet. So this symbol here, or this symbol here, is more the way you normally write it, is gamma from the Greek alphabet. So this process will happen whenever you get alpha or beta decay, and in some cases there's some isotopes that basically have these almost like natural excited states as well, that are quite long lasting, like molybdenum. That's so it can be made and transported around and used at various hospitals. But yeah, gamma decay basically accompanies all types of decay, and it's just that relaxation of the excited nucleus that's left. So that's it for the various types of decay. In the second part of this topic, we're just going to look at some of the properties of these alpha and beta plus and beta minus and gamma radioactive emissions. So, yep, that will be in the next video. Cheers.